Students, welcome. Today we are going to do KCC chemistry preparation tips. As you know, chemistry has got 3 papers: chemistry paper 1, chemistry paper 2, and chemistry paper 3. The code for chemistry is 233. Stroke 1 for chemistry paper 1, stroke 2 for chemistry paper 2, and stroke 3 for chemistry paper 3. So both chemistry paper 1 and chemistry paper 2 are theory papers, while chemistry paper 3 is a practical paper. So today we are going to start with the analysis of chemistry paper 1. So here we have Kcse chemistry paper 1, which is a theory analysis. So the topics that are tested in chemistry paper 1 are all the topics of the chemistry entire syllabus. So we are going to start with Form 4, that's topic 1. The topic name is Chemistry of Acids, Bases, and Salts. Learners, we have said all the topics that are taught in chemistry syllabus are tested in chemistry paper 1. But again, you're supposed to know that all the chapters of Form 4 are tested in chemistry paper 1. All of them, 99.99% are tested in chemistry paper 1. So you have to be very keen in the Form 4 syllabus or Form 4 chapters. You have to know it in your fingertips. So we are going to start with part 1, and the analysis we are going to do from KCSE 204 all the way to the 2021 KCSE. So we are going to start with part 1, where we are going to do KCSE 2004 up to 2006. So in our lesson today, it's going to cover the KCSE of 2004, 2005, and 2006. Okay, all the paper 1 questions. We start with number 1. We are told, starting with the aluminum sulfate, describe how a solid sample of aluminum hydroxide could be prepared or can be prepared. So here, we are told aluminum hydroxide. How are we going to prepare aluminum hydroxide? And you are supposed to start with the aluminum sulfate. So we are going to say, first of all, add aluminum sulfate, add aluminum sulfate, because we are told to start with aluminum sulfate, to ammonium hydroxide, ammonium hydroxide, ammonium hydroxide solution. Or instead, you can say add aluminum sulfate to aqueous ammonia or aqueous ammonia solution. Okay, full stop. This is a precipitation reaction, because when you take aluminum sulfate, then you react with that of ammonium hydroxide solution, what you are going to get will be ammonium sulfate and also aluminum hydroxide. So let's just try to see here. If you are having aluminum sulfate, which is a solution, then you have reacted with ammonium hydroxide, which is also a solution. What you are going to get here will be aluminum hydroxide plus ammonium sulfate. Ammonium sulfate. So all ammonium compounds are soluble. You have to know that. Then here we are having aluminum hydroxide, which is a precipitate. This equation is not balanced. You are supposed to balance it. So we don't have that time to balance, because we are just trying to see only what's happening. This is just a precipitation reaction. So here we are having a precipitate and one that's solution. So the next procedure will be filter the mixture. We filter the mixture. So to obtain aluminum hydroxide as a residue. Because as we have written here, aluminum hydroxide is a precipitate, that's a precipitation reaction, but sodium sulfate is a solution. So when we filter, we are expecting to get a residue and also a filtrate. So in this question, we are told aluminum hydroxide could be prepared. So describe how a sample of aluminum hydroxide. So we don't want ammonium sulfate. We want only aluminum hydroxide. So we said to obtain aluminum hydroxide as a residue. Then we are going to dry the residue between filter paper, the residue between filter papers, between filter papers. Even before this, we can say wash the residue with the water to remove the traces of the ammonium sulfate solution. Then after that, we dry the clean residue between the filter papers. So that's the end for that question, number 1. So we go to number 2. In number 2, we are told in an experiment, a student put equal volumes of mixtures of ethanoic acid in water and ethanoic acid in hexane in 2 test tubes as shown below. So these are the 2 test tubes. In each test tube, equal amounts of sodium hydrogen carbonate were added. Okay, so the question, if we go part A, we are told state the observation which was made in each test tube. So we start first of all, test tube 1. Test tube 1. In test tube 1, we are having sodium hydrogen carbonate and we are having a mixture of ethanoic acid and water. We know ethanoic acid is an acid, so here we are having water, which is a polar molecule. Water is a polar molecule. So therefore, this ethanoic acid will dissociate, producing hydrogen ions, which will react with the sodium hydrogen carbonate to produce now carbon dioxide. So, because we know when a carbonate or sodium hydrogen carbonate or hydrogen carbonate react with an acid, we get salt, water, and also carbon dioxide. So in our case here, we are going to form effervescence. So we're going to see effervescence occurred. Effervescence occurred. That's the observation that we are going to see in test tube 1. So what about test tube 2? So we're going to say test tube 2. So what do we have? What are the components that we have in test tube 2? We have sodium hydrogen carbonate, and here we are having a mixture of ethanoic acid, and we are having a hexane. So hexane is not polar, it's non-polar. So that means the ethanoic acid will be existing in a molecular form, hence does not have hydrogen ions, which will react with the carbonate to produce the carbon dioxide. So therefore here, there's no effervescence. So we say no effervescence. We say no effervescence. No effervescence occurred. No effervescence occurred. Good. That's the observation that we are going that was made in each test tube. So we go part 2. Part P. So in part P, we are told explain the observation in A above. The observation that we have said initially in A was, we said, test tube 1, effervescence occurred. Test tube 2, no effervescence occurred. Okay. To explain, we are going to say ethanoic acid in water. Ethanoic acid in water. Ethanoic acid in water ionizes. Ionizes, or we can say dissociates. Dissociates. Ionizes or dissociates in water to produce hydrogen ions. Hydrogen ions which reacts with sodium carbonate, hydrogen carbonate, hence effervescence occurred. Effervescence occurred. Okay. What about the side of ethanoic acid? So we're going to have the other side, ethanoic acid. Ethanoic acid in hexane. In hexane exists in molecular form. Exists in molecular form. In molecular form, hence no hydrogen ions. No hydrogen ions formed, hence no reaction. Hence no reaction with sodium hydrogen carbonate, hence no effervescence will be formed. So learners, during the exam, make sure you write sodium hydrogen carbonate in chemical in full word. Don't write in chemical symbol. So we go to example 3. Example 3, we are having 1 centimeter cube of soap was added to 2 test tubes, each containing water obtained from different sources. The lather produced in each test tube is represented as shown in the diagram below. So this question was in 2004, Chemistry Paper 1, question 23. Okay, so the question is, we are told explain why there is more lather in test tube 2 than in test tube 1. So here we are having test tube 2, here we are having test tube 1. So one of this water was soft water, and remember we said soft water is water that form lather easily with soap because they don't contain the calcium ion and magnesium ions, which makes the water hard. So the other one, it's having hard water, and you say hard water, we said hard water contains magnesium ion and also calcium ions. So one property that they have is they waste soap in scum formation. So here we have been told already that test tube 2 has more lather than test tube 1, as we even can see on the diagrams. So we're supposed to explain. So we're going to say test tube 2, this one, the one that's having more lather is the one that's having a soft water. So test tube 2 head soft water, which does not contain calcium or magnesium ions, hence forms more lather than test tube 1. Test tube 1, which had water, which contains calcium ion or magnesium ions in solution, which reacts with the soap, hence forms little or less lather. That's now the explanation, because we are told to explain why there is more lather in test tube 2 than in test tube 1. We know test tube 2 had soft water, so test tube 1 had hard water. Hard water contains magnesium ion and calcium ion, which reacts with the soap, thereby producing little or less lather. So we go to example 4. Example 4, we are told the setup below was used to illustrate the effect of hard water, the effect of heat on hard water. So we're having here hard water. Then we are heating using, or we are boiling using a Bunsen burner. Here we are forming substance A, and we're having there cooled water. So we are told name substance A. So we have only 2 types of hard water or hardness. One is called temporary hardness, then the other one is called permanent hardness. So temporary hardness is a hardness which can be removed by boiling, while permanent hardness is a hardness which cannot be removed by boiling. So if we are having hard water here and we heat using a Bunsen burner and we are going to get substance A, that means this hard water or this water contains temporary hardness, because temporary hardness can be removed by boiling. Again, remember, temporary hardness are caused by a compound called calcium hydrogen carbonate or magnesium hydrogen carbonate. So This calcium hydrogen carbonates and magnesium hydrogen carbonates, when they're heated, they decompose to produce their respective carbonates and also water and also carbon dioxide. That's why we're having substance A as our carbon dioxide. So this water, this hard water, it contains that temporary hardness. So name substance A, we are going to say carbon dioxide. Carbon dioxide. Full stop. That's substance A, carbon dioxide. Then part B, we are going to go to part B. So in part B, we are told to explain why the heating of hard water produced substance A. So we are going to say temporary hardness. Okay, this water contains temporary hard water. Temporary hard water contains calcium hydrogen carbonate. Calcium hydrogen carbonate or magnesium hydrogen carbonate. Magnesium hydrogen carbonate. Hydrogen carbonate which decomposes on heating to produce carbon dioxide. Which is the substance A. Okay, we are done with that question. We go to question 5. We are told zinc oxide reacts with acids and alkalis. So this question was in 2005, chemistry paper 1, question 5. So we are told zinc oxide reacts with acids and alkalis. Then we are told A, write the question for the reaction between zinc oxide and, from year 1, dilute sulfuric acid, from year 2, sodium hydroxide solution. So zinc oxide was one of the examples of amphoteric oxides. So we said we have 3 amphoteric oxides. One of them was zinc oxide, the other one was lead 2 oxide, and we're having aluminum oxide. These were the 3 amphoteric oxides. So what are amphoteric oxides? We said amphoteric oxides are oxides that react both alkalis and also acids, or are the ones that show both basic and acidic properties or characteristics. So to write, we are going to have zinc oxide, which is solid, reacting with dilute sulfuric acid, which is aqueous, giving us zinc sulfate, which is solution, plus water, which is liquid. That's the first question. The second question, we're having again zinc oxide, which is solid, reacting with 2 of sodium hydroxide, which is aqueous, giving us sodium zincate, which is aqueous because all sodium compounds are soluble, plus water, which is liquid. That's the 2 equations that we have. Then we are told what property of zinc oxide is shown by the question in A above. That's the amphoteric oxide property. So we are going to say it is amphoteric nature, or amphoteric property, or amphoteric oxide property. So we're done with that question number 5. We got to question number 6. We are told equal volumes of 1 molar monobasic acids, that's L and M, were each reacted with excess magnesium tanning. The table below shows the volumes of the gases produced after 1 minute. So we're having the acid L and M, which were monobasic acids. Then the volume of the gases, that's in centimeter cube, is 40 and also 100 centimeter cube. Obviously, this gas is just hydrogen gas, because when an acid reacts with a metal, we get hydrogen gas, or hydrogen gas is evolved. So that means the bubbles were, the volume of the bubbles were measured or recorded, and this is what we have seen. So from here, they are testing now the strength of acids. Okay, L and M, we are supposed to know which one is a strong acid and which one is a weak acid. So we check only the volume of the gas produced, because we are told if you compare the strength of acids based on the rate of effervescence or the volume of the gases produced, we are told strong acids produce large amount or large volume of gases when compared to the weak acids, because strong acids, they fully dissociate or ionizes, giving us many hydrogen ions compared to that other side of the weak acid. So we are told explain the differences in the volumes of the gases produced. So we are going to say M is a strong acid because it's the one that's producing large amounts of volume of the gas. So we are going to say M is a strong acid. It's a strong acid, hence what? Hence fully dissociate. Hence fully dissociate, or we say fully ionizes, one and the same. Fully dissociates or ionizes to produce, or say producing many hydrogen ions. Many hydrogen ions, having many hydrogen ions. Many hydrogen ions which reacts with magnesium tanning or magnesium ribbon, which reacts with magnesium to produce more volume of hydrogen gas, compared to or than L, which is a weak acid, hence or therefore, when hence partially dissociates or ionizes, producing few hydrogen ions, which reacts with magnesium, to produce less, or we can have even little volume of hydrogen gas, full stop. Because we know when a metal reacts with an acid, we are going to get salt and hydrogen gas. So here we are just considering the volume of the hydrogen gas produced. Okay, thereafter we are going to go to example number 7. In number 7, we are having KCC 2006 chemistry paper 1, question 11. So we are told water from a town in Kenya is suspected to contain chloride ions, but not sulfate ions. Describe how the presence of chloride ions in water can be shown. Okay, here we are not dealing with sulfate ion. Instead, we are supposed to look for or confirm the presence of chloride ions. So the reagents that we can use is silver nitrate. So if we use acidified silver nitrate, that means it is going to form no precipitate with sulfate ions. But we are supposed to confirm the side of chloride ion. That means it's supposed to show a white precipitate when that silver nitrate is added to the suspected water. So we are going to say as add, or you can say acidified, or when acidified silver nitrate solution is added to the suspected water, or to the water, we are told white precipitates. So if we see white precipitates are formed, confirming that water contains chloride ions. So number 2, but B of the question, we are told state one advantage of drinking hard water rather than soft water. Remember, we were having advantages of hard waters, but we are told one advantage of drinking hard water. So we use the one that was having it provides, or hard water, provides calcium ions, provides calcium, which is essential in strengthening bonds or in bond formation, That's the advantage of drinking hard water rather than drinking soft water. So we go to example 8. We are told below is a list of oxides. So this question is tested in 2006 chemistry paper 1, question number 14. So we are having a magnesium oxide, that of nitrogen 1 oxide, we are having potassium oxide, we are having calcium oxide, and also we are having aluminum oxide. Remember, in Form 1, under air combustion, we have done nature or types of oxides. We were having 4 types of oxides. One of them was basic oxide. Here we are having magnesium oxide and also potassium oxide to be a basic oxides. Here we are having again amphoteric oxides, which we have in our case aluminum oxide. We are having acidic oxide, but in our case we don't have acidic oxide here, and we had neutral oxides. An example of neutral oxide is nitrogen 1 oxide. Okay, so we are told select a neutral oxide. So the neutral oxide is nitrogen 1 oxide. So we are going to write like that. Okay, next we are told a highly water soluble basic oxide. So here we have 2 basic oxides. That's magnesium oxide and also that side of potassium oxide. Remember, group 1 oxides or potassium oxide is an alkali. What are alkalis? These are soluble bases. So that means it's supposed to be potassium oxide. So if you put your answer here as magnesium oxide, you will get wrong answers there. So C, an oxide which can react with both sodium hydroxide solution, and dilute hydrochloric acid or dilute sulfuric acid. So here they are just telling us select the amphoteric oxide. In our case, we have aluminum oxide, which is amphoteric oxides. Remember, previously we have said we have 3 amphoteric oxides. One of them is zinc oxide, the other one is aluminum oxide, and we're having that of lead 2 oxide. So we go to example 9. So example 9, this question is tested in Kcse 206, chemistry paper 1, question 19. So we are told part A of the question, starting from solid magnesium oxide, describe how a solid sample of magnesium hydroxide can be prepared. So here they have given us magnesium oxide, and they want us to prepare to get magnesium hydroxide. So the first step, we have to get a soluble salt, because magnesium hydroxide is an insoluble salt, okay, or an insoluble base. So the steps that were used to prepare insoluble salts, that's the one that we are supposed to undertake. So the first step, we are supposed to take this magnesium oxide and react with either hydrochloric acid, or you can react with sulfuric acid. So that means the product that we are going to get when we react with hydrochloric acid is magnesium chloride and also water, because this is a neutralization reaction. In case you react with sulfuric acid, you get magnesium sulfate plus water. So this is a soluble salt. So thereafter, you are supposed to react with a soluble hydroxide, because here they want magnesium hydroxide. So what we do, precipitation method, you can react with potassium hydroxide, or otherwise you can react with sodium hydroxide, so that neutralization reaction will happen. I mean, that precipitation reaction to happen. So that's what we are supposed to do. So the first step, we are going to say add excess magnesium oxide to warm dilute hydrochloric acid, or else you can use here sulfuric acid, hydrochloric acid, full stop. Then here we are going to get magnesium chloride and water, and we are having also the excess magnesium oxide, because we have put the magnesium oxide in excess. So we are supposed to filter. So we said filter the mixture to obtain magnesium chloride as a solution, as the filtrate, I mean. To obtain magnesium chloride solution as a filtrate. So we are going to get there magnesium oxide as a residue. the excess magnesium oxide to be as a residue. And the reason why we're using warm dilute hydrochloric acid is to speed up the rate of the reaction. So next, after that, we are going to add. We say add sodium hydroxide solution, or potassium hydroxide solution, whichever you like, solution. Okay. Or we're having sodium hydroxide solution or potassium hydroxide solution to the filtrate to be precipitate in order to precipitate magnesium hydroxide, to precipitate magnesium hydroxide. Then we are supposed to say filter and dry the residue, because the precipitate that we are talking about is just the residue. Okay, thereafter we are going to go to part B of the question, which is we are told give one use of magnesium hydroxide. So magnesium hydroxide is used as an antacid tablet. So we have here it's used as an antacid tablet, or antacid medicine in order to relieve stomach upset, or stomach acidity, or even we can say treatment of acid indigestion. In example 10, we have the question from 2006 chemistry paper 1, question 24. Part A, we are told complete the table below to show the color of a given indicator in acidic and basic solutions. So we have the indicator and we have color in acidic solution or acid solution. We have here basic solution, methyl orange, and they have given the other indicator as phenolphthalein indicator. So they are filled for us in the side of basic solution in methyl orange, and also acidic solution or acid solution in the side of phenolphthalein indicator. So this one we have done it in chemistry form 1 under acid, bases, and indicators. So methyl orange in acids was pink, and it was yellow in basic, and we are having orange in that side of neutral. Then phenolphthalein indicator shows colorless in acidic solution or acid solution, and it was showing pink in basic solution, and it was showing colorless in the neutral solution. So we have not been told or given anything about the neutral solution. We have filled our two spaces to earn the 1 mark. So part B, we are told how does the pH value of 0.1 mole potassium hydroxide solution compare with that of 0.1 mole aqueous ammonia? Explain. So here we are comparing again the strength of bases, because potassium hydroxide and aqueous ammonia are bases, and we are using now the pH value to compare that strength. Okay, so we said when we are using pH value, we said bases have a pH value of 8 all the way to 14. From 8 to 11, we were having weak bases. Then from 12 all the way to 14, we were having strong bases. So in our case here, the sodium hydroxide, potassium hydroxide is a strong base, and aqueous ammonia is a weak base. So therefore, we are going to see that 0.1 molar potassium hydroxide has a higher pH value compared to the aqueous ammonia, which is a weak base, hence has a lower pH value. That's what we are supposed to say. So to start, we are going to say 0.1 molar potassium hydroxide solution has a higher pH value than that of aqueous ammonia. So to explain, we are going to say this is because potassium hydroxide is a strong base, hence fully dissociates or fully ionizes, okay, while aqueous ammonia is a weak base, hence partially dissociates or partially ionizes, releasing few number of hydroxide ions, hence has a lower pH value. That's the end of our lesson.